Now we will look at the expectation maximization algorithm. So the EM algorithm assumes that we have some kind of membership, which is called HIT, which is defined as the posterior, so the probability of coming from group GI according to the XT and the parameterization. So this is whether we associate a given data XT to a group GI according to its parameterization, and the hidden variable observation, which correspond to the ground truth assignments of the data for a given group. So which is not known, which is not available, but which is used for our developments. So the log likelihood depends on the parameterization according to the association of hidden variable Z. Similarly, the association of hidden variable Z depends on the parameterization of our problem. So we get into the same chicken and egg problem that we had before with k-means. In fact, k-means is a special case of EM, expectation maximization. So we need to deal with that, and we will deal with that the same way we deal with it with k-means. And the point here is that I would say further complication of the problem is the fact that we don't know the real Z. The hidden random variables, so these are hidden, these are not available. So we need to look by optimizing over the likelihood expectation. So this is more fancy than what we saw before, but this is a way to really be able to estimate well things and estimate what would be the real Z. And as with k-means, we are not able to get into development of analytical equations directly because assignment H depends on the parameterization of the network, and the parameterization of the network depends on the assignment. So we need to be iterative instead of getting the analytical equation up front. And this is done through with the expectation maximization algorithm, which is called EM. So EM is simply implementing this. And so we have a step E, the expectation step. So it means to calculate the expectation of associating a group HIT. So the expectation of association to a group HIT according to current parameterization. And likewise, the step M, we get new parameterization of the next step. So parameterization at L+1, maximizing the likelihood expectation Q here. So we have Q, which is defined as the expectation. Sorry. So we have the expectation of the loss here. So we have these two here, and this corresponds to what we can guess from according to the Z, sorry. And then we also have the next step estimation of the parameters, which is given here. So at the step E, we have the given parameterization of step L, that is the likelihood expectation of another. So when we say, what is the likelihood expectation of another possible parameterization? So the point is to say, okay, let's say, okay, we have this one. So this is the one that we have currently. And so what is the expectation of a new parameterization that is relying on the current one? So we want to get a new parameterization here. We have the current one there. And so we are looking at the expectation of log likelihood here of getting a given parameterization according to the X, the Z, and also the previous parameterization. So developing this, we have a sum over the cluster, the groups, and the sum over the data as the expectation of ZIT times the log PI and plus log PXT. So the likelihood of getting a data from a group GI. And as such, we will make some developments. We will look at the label expectation over XIT given the data set and given the current parameterization. So we can say that, okay, over a full data set is here, we have the full data set. What is the expectation? Given that the XT are IID, so the XT are identically independent and identically distributed. So they are ID, so the expectation over the full data set is the same as the expectation over each samples. So this allows us to simplify from this with the full data set to that with only one sample at a time. And we know also that xit, even though we are not observing it, it is Boolean. So the expectation over z is basically the probability of z being equal to 1, given that zit is Boolean. Then we apply Bayes rules, basically. We know that this be converted the other way around. So instead of having this with the posterior of zit given xt and our parameterization, we will just apply Bayes, and that looks like this thing. And so if we develop this, we get into that formulation. So the only change between these two is the fact that we are either using PI or PGI, which are equivalent because PI is defined as equal to PGI. And as the rest, it's basically Bayes. And so we are falling back on the fact that all this is equal to the posterior. So all this is equal to the P probability of being from group GI according to XT and the current parameterization. And this is defined to be the HIT. So we need to interpret the HIT in some ways. HIT here is really defined as the expectation over the ZIT. So we don't see the Z, but we can get what we expect to be the most likely in terms of value of Z. So the expectation is the real values, and it corresponds basically to the probability that our X is coming from the group GI. So it gives a posterior probability that XT belongs to the group GI here. We can see this as a probabilistic observation of the hidden variable ZIT. And it allows us to make some kind of reinterpretation of a discriminant for clustering. Basically, it's like expanding the idea of having an H, the function H with our discriminant functions, linear discriminant, nonlinear discriminant. We always call this as a H. So, and this H is basically telling us whether or not it's coming from class 1 or not, according to its value sign. Here we are doing something kind of similar. The choice of using HIT here, it has been made purposely to make a recall of that notion of H function with classification. But here we don't have the ground truth. We can say that Z are somehow the ground truth, but we are not able to observe it. We only are able to observe something that is an expectation of ZI. So from some another point of view, we can see that HIT is a relaxed version of BIT, of the BIT binary membership of the K-means. So we are going from something binary, it's either from that cluster or not. HIT can assign this more smoothly and having samples that are in between 50-50, for example, between two clusters. And so the resulting likelihood expectation looks like this. So we have the summation over all samples or all clusters, HIT corresponding log the prior plus log of the likelihood. So we develop this a little further. And this is what we will use. We are kind of splitting the part with the prior from the part from the likelihood. So now we are looking at the step M. The step M means to find a new parameterization for step L+1, maximizing the log expectation that we currently have. So let's say that the best configuration is the one that is maximizing function Q here that we are developing there. So we look at the maximum where the partial derivative are equal to 0. And given that PI is a probability, we need to add some kind of constraint that the summation of PI is equal to 1 according to Lagrange method that we see several times before in the course, the Lagrange multiplier. So the partial derivative here is equal to that. And if we develop a little more, well, we need to know what to what corresponds here the parameterization. So the resolution here is made specific, in fact, to the density U. So if we are using multivariate normal distribution with that number of components, that's one thing. So we can develop this. But if we are using another distribution, we need to make new developments. All of this, the resolution of this equation equal to 0, required to know the exact shape because it will be highly necessary. So if we are looking now at first only for the prior probability PI, so this one we can get it without looking at the specific distribution. So we are saying, okay, let's make the partial derivative according to pi j here because we want to do it for all pi. So this is directly equal, given that we are only caring about this thing. This thing is kind of useless. So the derivative of this according to the pj, the summation over I, we just use the term where I is equal to j, and we set it here as like this is equivalent to hit, and derivative of log is 1 over the value that was in the log. So basically this is that minus lambda that stay here. It's that stay here that minus lambda because when we are making derivative of that thing here, there is only one case where pi is equal to pj, and this case is making us that the lambda can be used directly here as an element of the equation. And as such, if we go back, we just multiply both sides. So we just first move the lambda on the right here. This is what we have here, and then we multiply both sides by the pi directly, which seems to be impactless, but by moving this around, we can get into summing over all samples because we care about that. We sum over all samples, and we just have this kind of product between the pi, which is not that useful, but well, it's useful to simplify things because in fact here we have the statement over one specific I. Here we see that, well, if we sum this over all samples, no, so not samples, if we sum this over all classes, we get all groups. That's the right thing, sorry. So we have the right groups here. We are summing this over that. We have that thing, and all this is equal to 1 because the sum of the priors is equal to 1, and the divergence with itself is equal to 1. So let's go further. So we see that this thing is equal to that thing. And now that we have that thing, we know that summing the HIT over all groups is equal to 1. And we are summing, so this is what we have here. In fact, the sum over T is giving us T value because we have T samples. And basically that means that lambda is equal to n. If we go back to our equation here, we have that thing. We replace the lambda by this, so it is replaced here. And then we set that equal to 0, and basically give us that the pi is equal to the sum of hit divided by n. And this makes a lot of sense. We pass through the math to fall back to a case where we will estimate the centers not according to their real values because we know that some may be positions in some ways, but we are looking at the association given by hit. We are relying on this to look at the assignment of every sample to the different classes, different clusters, sorry, different groups. So we are looking at the assignments of the samples to the groups, and this is seen through the hit. And as such, we are evaluating the prior as the sum of this hit divided by the total number of samples we have in our database.